this alpha decay and beta decay, and we're looking now at this gamma radiation. So gamma radiation is energy radiation. So you've got, for instance, let's just take a particle, whatever it is. Let's just say it's got 21 and 50, for instance, like that. So it's got 21 protons and it's got 29 neutrons, if such an element exists. And what happens is it changes into a lower energy nucleus without the nucleus properties actually changing at all. So it will stay as 2150. The element is exactly the same. There's no change in the number of protons and neutrons except that they become more stable. Alright, so they give off energy out of this nucleus, and that nucleus gives out the energy in form of a gamma ray, or a photon of gamma, a gamma photon. So this is the symbol that we use for gamma radiation. Very high energy radiation. Now, we haven't looked at this formula in much detail yet. We will use it a lot. That E is equal to HF. Your energy of your photon. This is the formula for the energy of a photon. Einstein got his Nobel Prize for coming up with this idea that light can also be viewed as particles. Alright, so he came up with this idea, and these particles we call photons. So a particle of light. So sometimes we view light as a wave. It works very well. Other times light displays these particle properties. And the energy of that is given by this formula where H is Planck's constant. F is the frequency. So the higher the frequency, a high energy wave will have a high frequency. Correspondingly, it will have a very short wavelength. So your formula C is equal to frequency times wavelength, where C is the speed of light. These two are in an inverse proportional relationship. If you double the frequency, you've got to halve the wavelength. Alright, so as you increase the frequency, the wavelength must decrease. Okay, so that the speed of light remains constant as it is if we're looking at in a specific medium, like in a vacuum. It would be 3 times 10 to the 8. That remains the same. So it gives out this gamma particle. Now this gamma particle, gamma radiation, is very high energy. All it does with the nucleus itself is that the nucleus becomes more stable. They all just drop down deeper into an energy well, as it is. Now I can just to you can view it like that. They're in a deeper energy well. Their potential energy has decreased. We view it's actually gone deeper in. Yes, so it actually to split them apart, to take those particles apart, would now require more energy. So the bonds between those neutrons and protons has actually strengthened. Why doesn't it make sense?
Well, because the bonds between if you are closer to somebody, you can hold him better, right?
I just want to use this example here. If you've got a actually just this works well. So this is this idea here of with the polonium here. This gives an idea of the energy Now we view the energy. You're going to see this later on when we discuss things like looking at the potential energy. We actually view the energy when they are far away as being zero. Alright, so to take something out from here and splitting it apart is totally far away, we consider as zero. So in this case over here, if I reset the nucleus, you can see the energy here is actually higher. And then when it drops down, it drops deeper into an energy well. So we view this idea of the energy that's holding it together, almost like as a negative energy. Well, that is a negative. It's the strength of the bond, but the energy to take it out, to separate those particles making up the nucleus, to take them apart, that becomes, when they're apart, then there's zero energy. So when they're coming together, the bonding actually forms like this negative energy well. It's very much like an idea of as if you've got a deep valley, all right, like this, all right. We take the EP here as equal to 0. All right, now down here, there's a town, people are staying here, and you decide to go and live down there. Now you actually lose energy as you go down there because you give it out. You go riding down your bicycle, forms kinetic energy, goes all the way down, you crash at the bottom, deformation energy, breaking bones and so forth, heat energy, all of those things gets transferred. You're at a lower energy state at the bottom there. Alright, now we take this, if we take this energy here as 0, then this becomes 0. Now what actually happens with these is that when they're down there, when they change, they actually go deeper down. Alright, so suddenly there's a hole that forms over there. You get a sinking, the whole valley deepens, and you're now over there. Now you're actually at a lower energy, but to get you out there will take more energy. So the bonds that are actually holding you together are actually stronger. The strength of the bonds that are holding to pull you apart, to break these bonds so that you go out again, to be separated from all the other particles, the other nucleons, takes more. So there's a stronger bonding process that's taken place there. The park, sorry?
What factor makes the deeper? What factor? What factor of the atoms make the size deeper?
Well, it's the strength of the interparticle bonds. Now that's the strong nuclear force. So basically, as they get closer together, and there's more of those bonds. Remember, you may have one neutron with a strong, and that's bonding onto a number of ones. So if you've got 1 and 1, then it's just 1. But if you've got 3 or 4, then that nuclear force, one proton, is being bonded to maybe 3 or 4. So it's the strength of that strong nuclear force that's causing that strength of bonding.
Wouldn't it eventually go deeper and deeper and deeper and deeper into the valley?
Okay, I think we'll leave that for we can discuss that a little bit later. Okay, so that's your gamma radiation. Now, one other thing about the gamma radiation that I didn't mention but I did mention before, was that it's quantized. It comes out in very specific energies, and so from that we actually view that the protons and neutrons are actually in energy levels. They are at very specific energy levels within the nucleus, and so they can just change in very specific amounts, giving out energies according to those specific changes in energy levels. So you don't only get energy levels with your electrons, you also get energy levels within the nucleus with your protons and your neutrons.